Hello, everybody. My name is Maria Halusova. So Halusova as in hallucinations, which is ironic since I work with LLMs. I work at Unstructured.io, as Carter said, where we obsess over data, specifically unstructured data, of course. And this is what I'm going to be talking to you about today. Why unstructured data? Well, if you take any industry, finance, insurance, software development, up to 80% of data generated on daily basis is unstructured. PDFs, PowerPoints, HTML, Markdown, you have your maybe company policies in a wiki like Confluence and Notion, you have lots of emails, you have Slack messages, you have Discord messages. All of that data is unstructured, and that kind of data contains a lot of useful business insight, a lot of information about the internal workings of the company, about your customers, about your sales, about your products, about the decision making that goes on into different products and processes. And so this is the kind of context that would be extremely useful to RAG application. So this is the kind of context that you typically want to give to your LLMs and different either customer-facing RAG applications or internal RAG applications. However, unlike structured data, in its raw format, it's not very usable. So first step to leveraging this kind of data is to pre-process it and to make it structured so you could have it in your retriever, so you can search through it, so you can find relevant pieces of context. And that comes with a set of challenges, of course. And the first one is, if you think about it, typically, unstructured data is scattered across the entire organization. So maybe you have some PDFs in your S3 bucket, you have your Confluence or Notion with documents, you have some Google Docs, Salesforce records, Slack messages, and so on. And so the first challenge is to pull the important data from all of those different sources. And next, of course, unstructured data comes in a wide variety of native formats. I already mentioned PDFs, but you also have Markdown, HTML, and all the other different file formats. And so you have to figure out how to parse those documents, how to extract text from those documents. And every file type requires its own approach. Sometimes you can use rule-based parsers. Sometimes you will have to apply OCR and document understanding models and all kinds of tips and tricks to pull out the relevant context. And that's not all. The next challenge is the document layouts. Even if you think of text in a PDF, it can be just a plain wall of text, but you can have columns and different reading order. And then you may have images, you may have tables, charts, plots, and all kinds of visual designs and elements that sometimes contribute to context, sometimes do not. And so on top of that, you also can have all kinds of noise, especially if you're working with scans of documents, reports, contracts. If those documents are scans, then you have a whole new world of noise to deal with. And so building ETL pipelines to transform unstructured data into structured formats is very challenging. But that's what we do at Unstructured. That's what we love. We love figuring out how to access different data storage platforms through their APIs, how to parse different native formats, which rule-based parsers to use when, which OCR models to use, when to fine-tune OCR models, and how to deal with noise, how to standardize the outputs, which is another important topic to think about because you have all these different formats, but then as the output of each of those formats, you want to have a standardized data that you will load into your vector store. How to scale things, how to maintain. So it's very easy to end up with a pipeline jungle if you start from scratch. But let me show you how we pre-process unstructured data at Unstructured.io. So at Unstructured, we have streamlined the data pre-processing, and it looks approximately like this. So we've built a bunch of connectors that allow us to ingest unstructured data from 20 plus different sources, such as S3 buckets, blob storage, SFTP, Slack, Confluence, and so on and so forth. These are just a few examples. Once the data is ingested, we can partition the data using one of the 3 available partitioning strategies into standardized JSON format, which is going to be uniform across all data types. It's going to be the same standardized type of JSON with document elements and additional metadata. I'm going to talk a little bit more about partitioning strategies on the next slide. So we'll get back to that. And once the data is partitioned and it's loaded into JSON format, the next steps, as you have learned from the previous presentation, are to chunk the documents and to generate the embeddings. Once that is done, we can load the resulting JSON documents into your favorite vector store, such as AstroDB or any of the other 20 plus destinations that we support. So this way, you get from 20 different sources, 25 different file types, all standardized into a uniform JSON, chunked, embedded, and in your storage. When it comes to partitioning strategies, we currently have 3. And there is a fast strategy, which use rule-based parsers to pull out the text from the documents. And this is perfect for Markdown, HTML, Word documents. And it's going to be extremely accurate, very fast. But at the same time, you can also use fast strategy on certain PDF documents. If your PDF documents contain only text and it's not a scan of a document, you may be able to leverage fast strategy to get the fastest PDF processing out there. If your documents are much more complex and contain images and tables, you will have to use high resolution strategy, which is going to apply OCR and document understanding models to extract all the content out of the documents. And then there's auto strategy, which is going to automatically figure out based on the document type which one of the previous 2 strategies to apply. Looking under the hood, if we have a PDF like that, this is a page from an archive paper. Once processed, you get the JSON with document elements. Instead of giving you the wall of text, we split the document into individual elements. So for example, the first one here is classified as title. It has an element ID. And then you have the extracted text. Who validates the validators and blah, 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 blah. On top of that, every element comes with metadata, which can be very useful in a RAG application. Just a second. So these are the different element types that we categorize document elements into. You have your tables, titles, narrative text, list items, addresses, and so on and so forth. These can be useful to curate your data. For example, if you don't want to use any footers, you can throw them away. If you want to use only tables from your documents, you can do that as well. So categorizing the document elements into these classes helps to curate your data, but it also helps to preserve the structure of the documents. We also preserve the hierarchy of the document. So for example, here zooming in on one part of the same page, you get an element with type title called abstract. And then you get the next element, which represents the following paragraph. And if you see at the bottom of the second element in the metadata, you're going to notice that there's a parent ID, and it points to ID of that title. So we know that that text belongs in the section with that title. This is going to come in handy, super helpful when we do some smart chunking of documents. So by atomizing files into elements, Unstructured preserves document structure and hierarchy. Now you also have noticed that we add metadata to every element, and in the previous examples, there was only a few fields of metadata, but we try to extract as much metadata as possible from every element. So for example, if there are links in the text, we're going to put them into the metadata. If some text is highlighted, we're going to put that into metadata. If we used OCR, we can put bounding boxes for tables and images into the metadata. And some metadata is common for all types of documents. Some is specific to certain types of documents or certain types of elements. For example, if we are processing emails, then in the metadata, you may see the recipients, the senders. These emails will be in the metadata of the document. This is an element-specific example of metadata. Here I am extracting a table element, and in the text, you're going to get just the text from the table, but in the metadata, we're going to add text as HTML field, which will contain the plain HTML representation of the table. And in this manner, we can preserve the structure of the table, the columns, the rows, and you do not lose that valuable information. So at the bottom to the right, this is the same table, but printed out as plain HTML. Again, to summarize, from 20 different sources to 25 plus different file types, all ends up being this type of normalized JSON with document elements enriched with metadata. The next step, once the data is partitioned, is to chunk data. And you may be thinking, well, hold on a second, we already split the document into the document elements. Isn't that the same as chunking? It's not. In some cases, you may have very long paragraphs that still need splitting into smaller chunks. In other cases, you may have very small elements. For example, list items are individual elements, and you may want to merge them into a chunk. And we have developed our own chunking strategies that help you both split large elements and combine smaller elements without mixing context in the same element. When you do retrieval, you want to deliver to your LLM the most precise piece of information, the most relevant piece of information. And one thing that messes with that is when you mix context, mix different topics in the same chunk. In order to avoid mixing content, we offer several different chunking strategies, basic, by title, by page, and by similarity, that take into account that structure and that hierarchy of the document that we have preserved. For example, by title strategy will make sure that different sections will never be mixed in the same chunk. By page strategy will make sure that content from different pages will never be mixed in the same chunk. And by similarity strategy is useful when you don't really have clear structure in a document. And what it will do is it will run a quick embedding on two small text pieces before merging them to see whether they are similar enough to be merged. And if they're not similar, they will not be merged. And once the documents are chunked, the next step is to generate the embeddings. And Unstructured doesn't host any embedding models. Instead, we just integrate with different providers, and you can choose your favorite embedding provider, choose your model, and generate the embeddings with them. Now, how do you use this? There are 3 different flavors to Unstructured. There is an open source library that you can pip install into your Python environment and start prototyping. Open source library supports 25 different document types. All of those sources, all of those destinations, you can just start building whatever you want to build. Then there's the serverless API that has all the same functionality. Plus, we host our own fine-tuned OCR models and document understanding models. They're going to give you better text extraction quality on complex PDFs and image-based documents, which we don't offer these models in the open source library. Plus, we are going to scale your jobs, and we offer SOC 2 compliancy and a bunch of other production-grade functionality with the serverless API. And a little bit of a teaser, in a few weeks, we're going to be releasing our enterprise platform, which is going to be like the serverless API, but on steroids and with no-code or low-code options to build your workflows. Now, I know that everybody wants to see a little bit of code and how to actually build your workflows with unstructured. So let's go through an example. Suppose we have an S3 bucket with some PDFs, and we want to partition those documents. We want to chunk them, embed them, and load them into UnstruDB. How do we build a pipeline for the whole thing with unstructured? And it's going to be very quick and very easy. It's going to all fit in this entire screen. We're going to build a pipeline from different configurations, starting with the context, which is defined by processor config. This is where you define general behavior like logs, verbosity, directory where you want to store caches of intermediate results, things like that. The next three configurations are going to be for the source. Starting with the indexer config, this is where you specify the location of the files. In this case, that would be an S3 bucket. Downloader config is where you can change the temporary location where the documents are downloaded. And then the source connection config configures your authentication options, how do your passwords, tokens, secrets, keys, these things. Once the data is ingested, the first step is to partition the documents, and for that you need the partitioner config. If you are using the API, you will need to provide your key and the API URL, and this is where you can specify which partitioning strategy you want to use and any other additional parameters. Maybe you want to exclude some metadata or only keep a specific kind of metadata if you have some specific requirements for encoding, things like that. Next, chunking. By the way, chunking and embedding steps are optional. If you want to pre-process your data, not for RAG, but say to fine-tune your LLM, you can just skip chunking and embedding and just partition your documents and store them anywhere you want. In Chunker, you specify your strategy for chunking by title, by similarity, by page. You specify the chunk size, the overlap, things like that. Embedder. Embedder, you only need to tell it which embedding provider to use, which model to use. In certain cases, you will also need to provide your API key. And then 3 more configurations for the destination. In this case, it's the UnstruDB, so we need to specify UnstruDB upload stager config. The stager configs typically check, for example, if you have a schema in your destination, whether the schema matches your data, whether your data looks good enough to be uploaded. The destination connection config, your authentication options for that. And uploader config, this is where you specify your database, your collection, your namespace, things like this, where the data needs to be uploaded. And that's it. And you just call the run method, and your data is ingested from an S3 bucket, partitioned, chunked, embedded, loaded into UnstruDB, and ready to be used for your RAG application. Now on this slide, I have a QR code with a Google Colab notebook with an example of a working pipeline that if you're staying for the hackathon, you might find useful. It uses a local source, so you don't need to use an S3 bucket, but you can easily switch to whatever other source you would like to use. And it uploads the results of the pre-processing pipeline into AstroDB. And that's it. Instead of creating messy ETL pipelines for different sources with different APIs for different native formats, all you need to do is stack a bunch of configs, and it's going to run. Thank you. I don't know if I have time to answer any questions, but if not, you can find me on Twitter and ask me there. Or I'll be sticking around for the hackathon, so I'll be here if you need any help setting up pipelines.
All right. Awesome. Thank you so much, Maria. Another round of applause.